for this bell work. I've got the 77-degree angle. That's very nice because when you see that angle B here is through the vertex, which tells us that these two, they're congruent. Yeah, I know. It's been a while. Congruent just means they're the same, which means they're equal to each other, which means angle B also would be 77 degrees. Boom. So objectives for the day. I can classify triangles by side lengths, and then also I can solve for missing angles inside a triangle. Take 30 seconds and copy these down, please. All right, triangles. Just a closed, three-sided figure. Each side has to be straight. And by the way, you'll have to forgive my drawings. Like if I were to draw a triangle, something like this one, some students would say, hey, look, Mr. Sal, it doesn't close up right here. By the way, I wasn't doing this on purpose. That's just, I actually suck at drawing these. And then others of you would be like, Mr. Sal, that's a pretty curved line right there. Again, I suck at it, okay? But I did try. But what we see on this is that we end up with three angles on the inside here. This one, and this one, okay? Three angles on the inside. By the way, and I think we'll go over this, but sometimes they'll give these different markings like this to indicate that we're looking at three different angles. We'll talk about it, but right now it's just important that you understand that if the triangle does not close, it's not a triangle, which if I were to do this on purpose, you'd see something like this one. Right? Like, what the crap is that gap? Now, that's not because I suck at drawing, that's just because it doesn't close. And for the most part, we're going to be looking at straight lines, so don't expect any curvy lines as much as you want them, okay? But yeah, when it closes, it does give us these three angles on the inside. Looks very nice. If you have colors like this, it looks pretty even. Oh yeah, there we go, triangles and markings. Sometimes they'll show that the angles and sides are either congruent or different with those markings. So if we look at the drawing on the last slide, there we go. Now you could even color code these, right? You could say the red side is colored different than the purple one and the green one, which shows that they're different. If we're looking at sides, okay? So, but sometimes what they'll do is they'll give it a mark like this. And if I wanted to show that the purple side is different, I would give it 2 marks. If I wanted to show for some reason that the green one is congruent to the red one, and again, congruence tells us it is the same, I would give it the same mark. See this? Or if I wanted to show that this angle was congruent to this angle, I'd have to have the same markings, right? So I'd give this one 3 marks. Then I can see visually that these have the same exact measurement. Sometimes, by the way, they'll just give these marks on the inside like this one, and then we know that these ones are congruent. Or they'll give it something like this. And yeah, I mean, it looks like something out of, I don't know, some kind of hieroglyph or something from Samurai Jack, but it doesn't matter, okay? As long as you understand that the markings, if we see them, they will usually indicate differentness or sameness. Of course, if they've given us lengths, sometimes they just say, well, look, the red side here is 5 and the green side is 5, so they're the same. Okay, now we know numerically that they're the same. But if they use markings, it tells us the same exact information. Okay, well, with this, we can then classify our triangles by side lengths. And yes, you can classify them by angles, but we're not so concerned with that today. An equilateral triangle would have 3 equal sides. Okay, now I'm going to use technology to draw this triangle because I suck at it. So here, let's use this one. Now this one right here, we would say, are these side lengths the same? Well, without any markings, we can't really know. But if I put markings so that it's equilateral, then they'd all have the same mark like this. Okay, each of them has 1 mark, which again tells us that they're all the same. They are all congruent. That is an equilateral triangle. Equal kind of being the key word for me. That's how I remember that they're all the same, because they're equal, okay? Isosceles triangles. Let's, use some technology here, something like this one, okay? You know what, I'll use a different color, though. Make it real pretty. Well, if this was isosceles triangle, then I would give markings to two of the sides that are the same, like this one. And, you know, if some of you guys are like, I want to use 2 marks, that's fine, as long as the other one that is congruent has 2 marks as well. But this one only has 2 sides that are equal, which means that the other side here has to be shown as different. Or maybe, again, perhaps there is no marking there, okay? But this one is isosceles because 2 of the sides have the same markings. Now, I just want to reiterate this, but on the assignment, I do not believe that they're going to show markings, but in the future, we may see them. On the assignment, they're just going to give you actual lengths on these, okay? So isosceles, only 2 sides are equal to each other. I don't know if that means isos is some kind of 2-sided sauce, but there you go. You know, some kind of Latin or Greek background. I have no idea. But scalene triangles where no sides are equal. So if I were to give myself another triangle here, like this one, if I wanted to show that the 3 side lengths were different, I would use markings. But again, all the markings have to be different. So if I give this side 1 mark, then this one would have to have 2, and then this one would have to have 3. Boom. All right. Well, I guess that kind of looks like an angry face. Whatever. But that's scalene because we've shown through markings that all 3 sides are different. In fact, some of you guys may say, well, it looks like it's equilateral. Again, these are not proportional. Ignore how good or bad the drawings are. When the markings show that they're different, we have to assume that they are actually different. But this one would be considered scalene. Now, this is our first objective for the day, just classifying these by the side lengths. So it's important that you understand these vocabulary here. All right, in some triangles, you may see a 90-degree angled mark, like this one, okay? This one right here. And you could even say, well, we got 2 line segments right there, or, you know, go ahead and attach an arrow on that one. Now you got a line segment here and an array there. Just a little review of what we saw last time. It doesn't really matter. If it shows this mark, we know that it is a 90-degree angle. That's going to be important when we see the triangles. Not so much in this lesson, but later on, okay? But this marking, once again, if I were to do this by hand, which, you know, may not be so great, whether the drawing is great or not, if they show this marking, then we know that we're looking at a 90-degree angle. But they're not going to show in numbers 90 degrees. They're just going to show a little box like this. And this would then allow us to classify triangles by angles. And so you can double classify, one by the side lengths and then one by the angles. But again, we're not so worried about the angle classifications today. Just understand that if all 3 angles are less than 90 degrees, we call these triangles acute triangles by the angle. If one angle is 90 degrees, we call that a right triangle. And again, if it's 90 degrees, we're looking for that marking, right? So you'd have some kind of marking like this. If it's obtuse, then one of the angles is more than 90 degrees. It just means that, right, so if you look at a 90-degree angle here, and again, we're pretending like my drawing is really pretty and clean and nice. It just means that you may have an angle that's beyond that 90-degree angle right here, okay? Something beyond it. And then, of course, since it would be a triangle, yeah, you'd connect the 2 endpoints. Obtuse triangle. Now, I'm just going through these quickly because it may become important later, so we can review it later, but we're not classifying triangles with angles today. So, right here, classify the triangle by its sides. Okay, well, this is good. We got this set up so that we can just kind of refer back. Now, again, they're not showing any markings, but they are showing some decimal values, and they're not so pretty, but they'll do. So, remember, equilateral triangles, all 3 sides are equal or congruent. An isosceles triangle has 2 congruent sides, but a scalene triangle has no equal sides. So we're just looking for, I would just personally look for equality. And you may notice a pattern with the angles as well. So you could actually look at the angles yourself. But I'm looking at the side lengths. So is there any side lengths that I notice are the same? 8.23 and 8.23. However, 9.43 is different. So in this triangle, we have 2 side lengths that are the same. Well, that tells us then 2 side lengths are the same. That's isosceles right there. So we're looking at an isosceles, I spelled that wrong. Isosceles triangle. Now, by the way, instead of writing the word triangle, like we talked about last time, right, we don't actually use or write the word angle usually. Triangles are the same thing. We're going to use this, well, triangle symbol. This is an isosceles triangle. That's how this reads, isosceles triangle. Boom. This one, again, let's look for any side lengths that are similar. So I'm starting here on the left, 4.37, right? Well, the other two side lengths, 5.3 and 8.33, they don't match. Let's go to the next one, 8.33. We already checked with 4.37. Is it the same as 5.3? No. So 5.3 is different as well. This shows that all three side lengths are different. So we are looking right here at a scalene. I'm typing this one so I can triangle, like this scalene triangle. If I were doing this by hand, though, I would write scalene triangle. And that'd be good. Now, as big of a math nerd as I am, I enjoy this because it's so easy. Maybe that's a bad thing, but whatever. Still, classifying by its sides. Okay. Hey, look at this one right here. 5.7, 5.7, oh, 7.14. So this one's showing that only two sides are congruent. Again, congruent means they're the same. So this one right here, I'll do this one, I'll just write it out. This one right here, isosceles. And by the way, I am looking at the chart here because isosceles is a hard word for me to spell. If you know how to spell it by now, hooray for you, man. But not me. Now, this question usually comes up. It's not really significant, but some students are like, how would you write more than one isosceles triangle? It's not isosceles, it's isosceles triangles. Okay. Still classifying by its side, right? Hey, look on this one. 6.08 all the way around. All three side lengths are congruent. It's the first one we've seen like this. There we go, congruent. So this one right here, equilateral. Mr. Sal, spell equilateral without looking. Can't do it. Equilateral. Equilateral triangle. But we would just use a triangle symbol there instead of writing the word triangle. Of course, on the assignment, I believe it's just multiple choice kind of thing. Or what they'll do is, see these three dots right here? You got to move it. They'll say, make an equilateral triangle. Okay, you got to move these until all three numbers in the side lengths are the same. Now, I haven't pointed this out, but what you maybe have noticed with the angles, see when the three side lengths are the same, the angles are the same as well, okay? Or if we had a isosceles triangle where two of the side lengths were the same, you may have noticed that two of the angles were the same as well. If it were scalene, where no sides are equal or congruent, then all three angles were different. So technically, you can classify side lengths by the angles as well. But here we're actually showing the lengths are different. Okay, again, you can look at the angles, which we will, but right here with just classification, you can just look at the sides. So triangles, and you may have noticed this as well when working with the triangles here, but the three angles on the inside of a triangle create a supplementary relationship. What does supplementary mean? We talked about it last time, but I know that was a long time ago. They add up, all three angles are going to add up to 180 degrees, okay? This is true every time, all the time. All three angles on the inside have to add up to 180 degrees. If for some reason it doesn't add up to 180 degrees, it wouldn't be a triangle. It'd be something else, some other garbage-looking thing. So, the interesting thing here, they're supplementary, which means that if you were to combine all three of the angles, you would get a straight line. And I can demonstrate this, although possibly not so well. I'll use some technology, though, to kind of help me out. So if I had a triangle and I'm just this is just a random triangle, I'm not trying to make anything specific. And you could, this one right here, I would say it looks like it's acute, an acute triangle, so all three angles are less than 90 degrees. Perhaps I'm wrong there, but I got this purple angle. I'll make this one red and this one green, okay? I'm just differentiating by color instead of markings, although you could use the marks, okay? Well, what happens is if I were to, let's take this purple one right here, and if I were to separate it, and let's take this red one right here, and let's see if I can manipulate this just a little bit. Oh, well, you know, before I do that, let's take the green one as well. If I can, yeah, there we go. So I got all three angles, the interior angles, the inside angles from the triangle. But what happens is if I were to take all three of these and just manipulate them just a little bit, if I can. There we go. Let's say I wanted to combine it with this purple one right here like this, okay? And if I were to take the green one as well, let's move it over here. Well, if I were to combine it here, see this? And while I know I'm not so great at this, the purpose here is that you see that it creates this straight line, which again, this tells us that the relationship between the three angles of any, and you can do this with any triangle, cut it up, but they're always going to be supplementary. Okay? All three have a supplementary angle relationship. Well, the three angles in a triangle are supplementary. They will take away one of the angles, we have to find it. So here's what they'll do. Okay, they'll say the purple angle here perhaps is 45 degrees, okay? And then the red one is 80 degrees. Then you're gonna have to find this one right here. They may even make it an X. Okay, but what this does is it creates an equation that we can then solve. So what I'd say is you'd have the red angle, you got the purple angle, and the green angle. Well, if you were to add all three of these up, they have to equal 180 degrees because it's supplementary. Of course, on this one, you'd know 45 and 80, but you just solve it like your regular equation, combine the like terms, principles of equality, boom, done. Now, some students take a little bit of a shortcut on this, and I think you may notice what it is once we get started. Okay, but I'm going to keep using the equation to do this. All right, so I got this 111 degree angle, I got 41 degrees, and then this one that's unknown. Nice. Well, if I were to take the red angle, and the purple angle, and the green angle, and add them together, as it turns out, I should get 180 degrees. It has to be 180 degrees for this to be a triangle. But we know the measurement of that red angle right there. It's showing 111 degrees. So I don't really need the symbol there. I just use 111. And then the purple one shows as 41 degrees. So again, I can actually replace that with a number, 41 degrees, which means I'm just solving for this angle. I will call it angle X. Okay, there's an equation that we can solve. And so I will solve it by combining like terms first. 111 plus 41, 152 right there. Of course, it didn't really do anything with the rest of the equation there. So plus angle X equals 180. And now we're at the point where we'll use the principle of equality to solve for X. I'll do this by subtracting 152, right? That will just give us the angle X minus 152. That will zero that out. I'm left with just angle X, which is what we wanted, which equals 180 minus 52. Ooh, that's 28. 28 degrees, boom. So we did find the actual measurement of angle X, so I will include the degree mark right there. And as much as you want it to do more, it's done. Last one, so just like we talked about on the last assignment, or lesson rather, but some students will just take, they know, all right, all three angles is 180, and then they'll just say, I know I got to just subtract those other two angles, the 41 degrees and then the 111. This, of course, is something they would just put into their calculator, and then they would get the 28 degrees. Okay, again, I don't really care how you do it, but the answer should be the same in the end, no matter what. So you can use that same method on this one, but again, I'm going to stick with the equation just to have some consistency here. All right, so the equation, again, I'll try to color code these. I got 38 degrees, so that's my red angle. I got 83 degrees here, that's my purple angle. And then again, angle X, right, which is in green for me. if you were to add these together, you should get 180 degrees, right? Well, we know the measure of the red angle is 38. And we know the measure of the purple one is 83. So I'm solving for the green angle, which is labeled with an X, so I will show it as angle X. Well, we see that this one's going to solve exactly the same way as that last one, 38 plus 83, which I believe is 121 right there. And then, of course, we'd have to add the X, which equals 180. And now we're looking at an equation to solve. No problem. Just subtract 121 from both sides. Okay, this will give me angle X equals 180 minus 121, 59 degrees. Okay, and yeah, again, this is an actual angle we're solving for, so I will apply the degree symbol. Now you could check 38 plus 83 plus 59. Put that in the calculator, solve. Yeah, it should equal 180, right? And so that is true. Or you could say, look, we know it should be 180, just like I was saying on that last example. Some students would just, in the calculator, subtract 38 and subtract 83. And yeah, you should still get that 59 degrees. Same answer, I guess 2 different methods. So on this one, yeah, we got this angle X right here, still unknown. I got my red angle, for me, is 63 degrees. This one right here, though, man, this one, they're not telling us what the degrees are numerically, but they did with the box. This is 90-degree angle right there, okay? Again, because of that marking, we know it's 90 degrees. And sorry, this degree mark kind of looks like a 0, but it's not 900, it's 90 degrees. Okay, so for these 3 angles, if I were to take the purple angle, which is 90 degrees, and I were to take the red angle, which is 63 degrees, and then my green angle, which is angle X, if you were to add these together, all 3, you should get 180 degrees. Okay, but again, we know some of these values. The purple one is 90 degrees, and the red one is showing at 63 degrees. Hey, principles of equality, that should do it. Actually, combining like terms first, right? So that appears to be 90 plus 63 is 153 degrees. So if I were to add that to my X, I should get 180. So final principle of equality here. Just subtract 153 from both sides. Okay, and that will zero that out. So I'm left with my angle X, which is exactly what we're solving for. Is going to equal 180 minus 53. Let's see, 27 degrees, pretty small. That's still doable. And again, if you did 180 minus 90 minus 63, you should get the same answer. Hooray for us. Well, we remember these 2 beautiful objectives. I can classify triangles by side lengths, and also I can solve for missing angles inside a triangle. Both objectives we went over. Hopefully you feel pretty good about them, because if not, the assignment's probably going to suck. But good luck.